again. This is part 7 and episode 26. And we're still talking about chapter 7, which was about groups, context, communicators, and caching in MPI. So we're going to continue from where we left off. And we're going to talk about this new operation, which is MPI inter-com create from groups. This is also, you remember, similar to MPI com create from group. We were creating basically an intra-communicator by passing a basically a group of processes, whatever processes. We didn't need to basically provide a pre-existing communicator. Here is also the same. If you use MPI intercom create, you gotta pass in a peer communicator, which the peer communicator, we said that it's the communicator that basically holds both of group A and group B. But here, MPI intercom create from groups, you don't need to pass in any communicator. You gotta pass in a local group with the leader of that group. You gotta pass in a remote group with the leader of that group. Then you gotta pass in a string tag, an info handle, and then error handler, and then you get your new intercommunicator. And again, notice that rank of local group leader in local group, and this is also rank of remote group leader in remote group. This is super important. These are relative to whatever they have in their own groups. So that is super, super important to notice. And then every parameter here is an input, as you can see here. And then finally, the last thing is the intercommunicator handle is going to be the output. And then again, the string tag is basically a const char star, which is a C style string. And then the error handler is of type MPI error handler. We haven't talked about error handlers, and we were using in one of those previous examples, we have used MPI errors are fatal. It's going to be the same also in this example. We had an example for this one. Yeah, we have MPI intercom create from groups. Let me see. Vim MPI. Oh my lord. I got to go back. MPI intercom create from groups.c. So before going to the example, let's take a look at the rest of the stuff if there is any explanation left. So this call creates an intercommunicator. Unlike MPI intercom create, this function uses an input previously defined disjoint local and remote groups. This is very, very important that those local and remote groups must not be overlapping. The calling MPI process must be a member of the local group. The call is collective over the union of the local and remote groups. All involved MPI processes shall provide an identical value for the string tag argument within each group. All MPI processes shall provide identical local group and local leader arguments. Wildcards are not permitted for remote leader or local leader arguments. The string tag argument serves the same purpose as the string tag argument used in MPI com create from group. So it differentiates concurrent calls in multi-threaded environments. So we have seen that explanation before. And then you know that, for example, the string tag length has an extreme, has a boundary. And then for C, you need to always consider the null terminating character and stuff like that. We don't care about those stuff right now. Okay, the next one is the merge, but let's jump into the example itself. These things are quite obvious. Then we have the world group. Then we have the corresponding processes in MPI com world. And then we have a local group, which we, let's say, initialize it with MPI group empty. And then for remote group, we do the same. Why we do that? Because these basically groups are seen by all processes. And then we initialize this local leader to be 0 and remote leader to be 5. But this is not important. This can be any values in there. But for processes, this is our group B. Processes 2 and 3 are going to be in one group. So we have an isolation block here. So if your rank is 2 or 3, then your local ranks is going to be 2 and 3. Your remote ranks is going to be 4, 5, and 7. Those are the processes in group B, which is the else if statement or the second portion of the if isolation block. So this is going to be as processes 2 and 3, your remote ranks are going to be 4, 5, and 7. And then MPI group include, then you put local ranks, those 2 and 3 into this local group. And then you put with this MPI group include constructor, the group constructor, you put 3 processes with ranks of 4, 5, and 7 as remote group. And then you pass in your local leader to be 0, and your remote leader again. This rank that you pass in here must be relative to the rank of the processes in group B. So when I pass in 1 here, I could have passed also 0, which corresponds to process 4. But I intentionally put it 1 to distinguish between the 2 here so that you understand the difference between the two. When I say local leader is going to be 0, it means that process 2 in group A is going to be the leader of group A. And in group B, the remote leader is going to be actually process 5. That's the root process in group B. And then for processes 4, 5, and 7, your remote rank, now the positions are going to be reversed, sort of. So now your remote ranks, you see that here local ranks were 2 and 3, but here remote ranks is going to be 2 and 3 because we are relatively seeing it from the side of group B, or processes 4, 5, and 7. And your local ranks are going to be 4, 5, and 7. And then again, you use these constructors, group constructors, to create your local group and your remote group. And after this basically thing is done, here I put the call to this MPI intercom create from groups accessible to everyone. So this means that all processes, not only process 2, 3, 4, 5, and 7, but let's say if I'm using 8 processes, processes 0 and processes 1 are also, and also process 6 are going to see also this call here. But the difference is that this inter-communicator is going to be MPI com null for those processes, for process 0, for process 1, and for process 6, which are not part of these groups here, right? So, and then I ask, I have another isolation for those processes which are proper processes, which means that they are part of group A or they are part of group B. Then I want, for example, rank 2, which is inside group A. I want to basically test whether my intercommunicator is an intercommunicator or an intra-communicator. And then the root of that group is going to basically print the result for me. And then I have MPI com remote size. So this is going to give me the size of group B, which I hope this should give me basically group A remote size equals 3, because we have 3 processes there. Group B does the same. It does the test for intercommunicator, whether it is intercommunicator or intra-communicator. And then it asks for, or queries basically the remote size, which is the size of group A, which I hope that I get 2, value of 2 here, because I have 2 processes in group A. And then all those valid processes need to free the respective sort of resources that were allocated, which contains that intercommunicator which was created a second ago, and those groups, local and remote groups. Okay, so let's do an MPI CC MPI intercom create from groups.c, and let's run it with 9 processes. You see that we have so intercom flag for being intercommunicator is 1, so that is true. It means that it is an intercommunicator. The remote size with respect to group A, that's the size of group B, is 3. It is correct, as we expected. And this one also shows 1, and since we had 2 processes in group A, we have the value of 2 here. Next one on the line, before going to the next one on the line, we had also MPI intercom create from groups extra. So in the previous call, you see that I put that operation. So let me bring this thing up. So this is the previous example on the left-hand side. You see that this call, MPI intercom create from groups, was accessible to all the processes in MPI com world communicator, right? However, in this example, it is exactly the same example, but you see that only processes 2 and 3, or processes in group A, they're going to call this MPI intercom create from groups with the corresponding correct sort of parameters. And then processes in group B, they're going to have this call. No other processes are going to see this call. So what does it mean? It means that this MPI intercom create from groups can be called from all processes in MPI com world, but it also can be called from only the processes which form group A and group B. And maybe it is more, let's say, optimized, or let's say you're going to have better performance if you isolate it only within processes that they are part of group A and group B, because the rest of processes, they have no reason to basically do this dubious operation. So that is the only difference, that extra which was added at the end. So this example is exactly similar as the previous example, but I'm gonna compile that and show it to you. And with 9 processes, it is exactly showing the same results as the previous one. Whoops. Okay, next one on the line is MPI intercom merge. Do I have any example for this one? Yeah, I do have. I don't know why I didn't mention. Okay, let's put this thing here. C MPI intercom merge. Yeah, I forgot to add this thing here. We do have an example for this one. You got to pass in your inter-communicator, and then you have a high value here, which is an integer. Take a look at it. And then we have our new intra-communicator. Which is going to be our output. What is high here? It's the ordering of the local and remote groups in the new intra-communicator. So let's take a look at this. It says all MPI processes should provide the same high value within each of the 2 groups. So this means all the processes in group A should provide the same high value, and all processes in group B should have should provide the same value for high. It doesn't necessarily means that the high values between group A and group B have to be identical, but it means that between those processes in group A, it has to be the same value, and between processes in group B, it has to be the same value. If MPI processes in one group provided the value high equals false, and MPI processes in the other group provided the value high equals true, then the union orders the low group before the high group. So this is quite easy. But if both of those MPI processes provide the same high argument, so let's say both of them provide true, for example, then the order of the union is going to be arbitrary. This call is blocking and collective within the union of the 2 groups. I think it's quite easy to understand. And then we have a bunch of examples, which we have our own example here. MPI intercom merge. So this thing is similar to before. Then we need to have an inter-communicator. Here is how we do that. We have the splitting mechanisms. And then we have an original inter-communicator, intercom. Now I want to combine inter-communicator groups A and group B to create a new intra-communicator. So since we have created our inter-communicator from all processes in MPI com world, so the join of those, or the merge of those groups A and B, again, is going to create a communicator, an intra-communicator, which is similar to MPI com world. So you got to pass in this MPI intercom merge. You pass in your inter-communicator, you pass in the value high. So here all the processes are providing the value of true or 1. So this means that the order in the order of processes in the intra-communicator, the resulting intra-communicator is going to be arbitrary. And then we put an if here that if it's not null, then you're going to print some information. For example, which process do you have, your rank, and then what is your intra rank in that sort of intra-communicator which we created. So MPI-CC, MPI intercom merge, it was a very simple example. So let's run it with 9 processes. You see in this case, proc 1 in MPI world is corresponding to again, proc1 in intra-communicator. Proc3 corresponds to proc3, and proc4 corresponds to proc4. Although that it was said in the standard that it's going to be arbitrary, but you see that MPeach basically has this equivalence between the MPI com world and also the intra-communicator that we have created. So these are examples. We don't care about them. We had our own example. So the last part of this chapter is about caching. MPI provides a caching facility that allows an application to attach arbitrary pieces of information called attributes to these three kind of MPI objects: communicators, windows, and data types. So caching are those attributes that you can pass to your objects are only accessible within these three objects: communicators, windows, and data types. So it's three objects, but we haven't seen one of them, right? So communicators, we have seen them. Data types, we have seen them, but we haven't seen windows. So that is a subject of another sort of chapter. So we're not going to comment on windows yet. So more precisely, the caching facility allows a portable library to do the following: pass information between calls by associating it with an intra or inter-communicator, window, or data type. So you can use it for the purpose of passing information. Quickly retrieve that information. You can pass it. You can quickly retrieve it. And be guaranteed that out-of-date information is never retrieved. The caching capabilities in some form are required by built-in MPI routines, such as collective communication and application topology. Defining an interface to these capabilities as part of the MPI standard is valuable because it permits routines like collective communication and application topologies to be implemented as portable code, and also because it makes MPI more extensible by allowing user-written routines to use the standard MPI calling sequences. We have a rationale here. In one extreme, one can allow caching on all opaque handles. The other extreme is to only allow it on communicators. Why? Because, okay, caching also has some price associated to that. It says that caching has a cost associated to that. One extreme is we only use it on communicators. One extreme is we use it on all sort of opaque objects that we have in MPI. But what is the difference? Here's the difference that it says. It says caching has a cost associated with it and should only be allowed when it is clearly needed and the increased cost is modest. This is the reason that only Windows, data types, and communicators are having those basically caching capabilities. Okay, functionality. Attributes can be attached to communicators, windows, data types. Attributes are local to MPI process and specific to the communicator to which they are attached. Attributes are not propagated by MPI from one communicator to another, except when the communicator is duplicated using MPI com dupe or MPI com idupe or dupe with info or idupe with info and stuff like that. So, it says, advice to users: attributes in C are of type void star. Typically, such an attribute will be a pointer to a structure that contains further information or a handle to an MPI object. Another sort of hint. And then we go with, so with this, it says the caching interface defined here requires that attributes be stored by MPI opaquely within a communicator, window, or data type. Access or functions include the following: obtain a key value used to identify the attribute. The user specifies callback functions by which MPI informs the application when the communicator is destroyed or copied. And store and retrieve the value of an attribute. That's how basically the system of caching works. So you're going to have callback functions in two scenarios: once you are destroying objects, once you are copying objects with MPI com dupe, MPI com idupe, and dupe with info, and idupe with info. Okay, so here, and it says also they are all MPI process local. So the first section is going to talk about the caching capabilities and how you can assign attributes and key value pairs to communicators. And then the next one is going to be about windows, which we are going to skip that because we don't know already what windows are in MPI. And then the last section is going to be about data types. So we have an example here, see MPI create key val simple, and then we have also another one with sort of advanced, but is not that crazy. So MPI create key val. So you got to pass in your copy attribute function. So this is your callback function for copying operation. Then you're going to pass in your delete attribute function. This is the callback function for delete operations when you are destroying objects. Then you have your key val or your attribute, and then you have an extra state which you can also use it in your callback functions. And we're going to see the usage of that extra state, for example, in the advanced example, how you can use it. So all these things are input parameters, and then the key val is going to be that attribute that you basically create, and it's going to be an output. So MPI create key val. You see that the first argument and the second argument, it has a very sort of a strange type, which we haven't seen it. It is MPI copy attribute function star. That's a function pointer type. And also this one, MPI delete attribute function star. It is also a function pointer type. So these are those callback functions that we're talking about. So it says that once allocated, the key value can be used to associate attributes and access them on any locally defined communicator. The C callback functions are like this: type def int MPI copy attribute function. So this is sort of the signature of a user-defined callback function. It should follow always this sort of arguments. It has to always have one output, which is an integer. It has to always have a communicator, MPI needs to have a key val, it needs to have a void star extra state, it needs to have a void star attribute val in, it needs to have a void star attribute val out, and also a flag. So this function pointer type that has this sort of type def, you know that it's like a function pointer type in C. And we have also another function pointer type which is defined in C for the delete operations. This is sort of the signature of the function, of that user-defined function, if you want to basically have one for your callback function in delete operations. And delete operations, for example, you can explicitly delete them. We're going to see it later. Or you can use, for example, the routines, the free routines. When, for example, you say MPI free, that communicator is going to be freed. And if you have an associated attribute attached to that communicator, since you freed that communicator, it will automatically also call your callback function for delete operation as well. Okay, so it says the copy attribute function is invoked when a communicator is duplicated by MPI dupe, MPI idupe, or MPI dupe with info, or idupe with info. We already knew that. The copy callback function is invoked for each key value in all communicator in arbitrary order. Each call to the copy callback is made with a key value and its corresponding attribute. If it returns flag 0 or false, then the attribute is deleted in the duplicated communicator. Otherwise, flag 1 or true, the new attribute value is set to the value returned in attribute value out. The function returns MPI success on success and an error code on failure. So that means that the operation that is basically running behind the scenes, either it's going to be the MPI dupe or MPI idupe or dupe with info or whatever, it's going to fail. The argument copy attribute function may be specified as MPI null copy function. So these are like some predefined values that you can pass in. If you pass in MPI null copy function, or if you pass in MPI, so 24 minutes is over. I'm going to finish this section and then we're going to continue in the next episode. So if you pass in MPI null copy function or MPI dupe function from either C or Fortran, it means that in the first case, this function does nothing other than returning the flag 0 or false. That is MPI null copy function. So there is no copying happening behind the scenes. Or So it basically does this flag equals false, and also it returns MPI success. So there's no copying happening behind the scenes. But if you pass in MPI com dupe fn, so dupe function is a simple copy function that sets flag equals to 1 or true, returns the value of attribute value in attribute value out, and returns MPI success. Okay. These replace the MPI1 predefined callback MPI null copy fn and MPI dupe fn. So previously back in MPI1, they had these names, predefined names, but now their name is MPI com null copy function and MPI com dupe function. So this point is very important. I would rather keep it for the next episode. I'm going to stop here and then we're going to continue in the next episode.